Well, good morning, everyone. My name is Eric Rounds. I am a remote sensing specialist for the Forest Service. I work at the Geospatial Technology and Application Center in Salt Lake City, and I've been working with Nicole and Emma on this ecosystem services project for about a year now. And I'm basically going to be demoing this tool or pair of tools that you've heard mentioned a couple times today. And I'm going to start with this desktop tool. Essentially, it's a Python script that is meant to take these two different data sets that we've been talking about so far, those modeled ecosystem services data. They're essentially modeled for different percent cover losses, and the ravage data. And that is a Forest Service derived product. Ravage stands for Rapid Assessment of Vegetation Condition After Wildfire, kind of a mouthful, but it basically provides immediate assessments of the impact of fire on vegetation. And let me just kind of show you around the data that we have. This is my folders that I have set up here. When you actually run these tools, you don't have these many, but I've set up a couple of subfolders that are used for this demo. Here we have all of those ecosystem services that I've been provided thus far. These are all recharge for different water years, and this ET2, ET0, these reflect the different modeled cover losses. Now, if we keep scrolling down, see all of the other years that we have recharge, and then we get down to runoff, and finally down to sediment export and sediment retention. Please let me know if I'm going too fast. I'm not sure if there's a delay in the kind of transfer of things here. So that's the one of the inputs that we need. And the next is our fire data, basically our ravage data. And now right here are the subfolders that contain, just for our demo, 3 different ravage data sets for 2009. This one is the sheep fire, and we basically need 3 different products in this folder. One of which is a fire perimeter, just a basic shapefile, and that will contain some of the naming conventions that we'll see later. Basically, when we upload the outputs from this tool to the website that we've developed, it'll gather information from the attribute table relating to the fire name and the fire year. We also have this metadata file here that just tells us some more information about the year and exact date of the fire. And then we have this CC product, and that's our canopy cover loss product that Ravage creates. Ravage creates a lot of different data sets, and we only need getting a lot of feedback on my end. Oh. Can you all hear me just fine still?
Hear you fine.
Yeah, we can hear you.
Okay, great. So let me move on here. Basically what we've done is created a couple of Python scripts that coordinate the processing. So basically what we want to do is combine these two data sets. So the ravage data is telling us here that we have 100% cover loss. Now we want to pull from the modeled data set that has been modeled for that 100% cover loss for runoff, recharge, and sediment export. And really what we need to do this is some basic installation files. Just an OSGeo is something you don't need to know much about, but it basically brings in a lot of the capabilities to your computer that allow us to do sort of geoprocessing on your desktop. So the first part of this process is to have these batch files, these 4 files. There's really very little you need to know about them in order to run this. The only file here that you would actually edit is this parameters file. And all you need to provide here are a few file paths. Close this. So here, there's a lot going on in the script, but all we need to focus on in this section here is where we're telling the script basically where our fire directory is, so where that ravage data is, and our ecosystem services directory. So those are 2 of the file paths, and then a basic outputs folder. And I've created a manual that essentially walks people through not only downloading and accessing ravage data through our standard Forest Service ravage website, but also through an FTP site where we have California ravage data dating back to, I think, even the 80s. I think you folks are unique in that California is the only state that has data going back that far. So that's something nice. And in this case, you're able to get data going back to 2000, which is when kind of the earliest extent of the ecosystem services data. Now, once we have all of these directories here, we can simply save our script and use these batch files here to do our processing for us. We have our outputs folder, our fire data, and our ecosystem services raster. All we have to do is double-click this OSGeo4W, and it basically opens up a command prompt and connects to the functionality available within OSGeo. Once we've done that, we simply drag and drop the other batch file here. You can see a cursor's blinking, and it's really as simple as pressing enter on your computer. And then it will start cycling through all of that data you give it. First thing it's going to do is identify all the fires that you have. So I've only provided it with 2009 fires, of which we have 3 fires. And it will go through each of these fires and identify the ecosystem service rasters that match that same year. And it will create products. If we have data for sediment retention and sediment export, it would create the products. I think in this case, we only have recharge, runoff, and sediment export. Now again, this is about 3 different fires that is processing, and it should take 1 to 2 minutes to create these products. And I'll show you in a minute what these products look like. Essentially, the outputs include 2 folders for each respective fire, one of which is just an intermediate file that is created by the tool. It reprojects the data and clips it to the fire boundary. Recognize that the ecosystem service rasters that we have here are for that entire SEVIS study area, the socioeconomic vulnerability assessment study area. So we need to clip it down to our fire perimeter first before we can start kind of stitching together our pre and post fire data. Now that is the basic goal of this tool, is to create post-fire data that integrates the ravage data. So essentially we're looking at the different severity across a given fire perimeter and using the modeled raster data sets to kind of piece together a single raster that gives us post-fire impact that we can then summarize and get a whole lot of statistics on. It'll also spit out a pre-fire raster, so we'll be able to do an assessment of what the pre-fire provision of ecosystem services were versus the post-fire provision of ecosystem. Now it should be about done. That means we're done here. And we go into our outputs demo, where are those folders I talked about. If we look inside them, these are the intermediate files. We have a bunch of reprojected data, some folders that contain the clipped information. But again, this is just an intermediate file. This is not something we actually need to focus on. These 3, however, are the ones that will be uploaded directly to our website. So if we look inside this, we have a few different files. We have the input ravage data, including the perimeter, so the sheep fire with a perimeter here, our metadata text file, and our original canopy cover loss file. Now these have been all pre-projected into a geographic coordinate system as to be better suited for a web environment. And in addition to those initial ones that are basically just copies of our input data, we have a JSON file. Now this just basically contains all of the statistics that we'll display on the website. Next we have a few sets of ecosystem services pre and post fire rasters. So here we have the recharge post-fire raster and the pre-fire raster, and the same things for runoff and sediment export. Now we don't even need to unzip this file. You'll notice here that it is zipped up automatically. And what we will then do is go to our website. So as I think Hugh mentioned earlier, this website is currently hosted on our servers. We had initially started building it on the GTAC servers. It was more efficient just to build it on our own servers here at GTAC. In the long term, we're definitely going to want to find a different place to have this website hosted from. Not only because that website would probably enable us to add a bunch of different capabilities in terms of web mapping services, but it would also hopefully be outward facing. Currently, this is just a Forest Service only website. If you are outside of the Forest Service and not connected to FS Web, you cannot access this. And it's kind of difficult. We have to jump through lots of different hoops in order to get outward-facing websites for the Forest Service. So ideally, we would find a kind of separate avenue to take. But this is the initial interface that you'll see when logging in here. If you're an administrator.
Can I just step in for a second? I just want to mention that the process we just saw is the process we would use to add new fires. Many of you will be interfacing with this, this server and this outward-facing website. And then, you know, people like me or the GIS specialist would be doing the processing of new fires and pulling in ravage data. So this tool will be flexible moving into the future with new fires. But there are fires currently uploaded, and Eric will show you that now.
Yes, thank you, Nicole. And it would be really easy once you have the ravage data. The ravage data is produced very quickly post-fire. They typically look for Landsat imagery as close to the end of the fire date or the fire as possible. And then as soon as the folks at UC Davis produces ecosystem service rasters here for that given year, we can then begin creating those new outputs to assess the impact of fires on ecosystem services. You go through that same process, create new data sets as we move forward in time and as new model data and ravage data become accessible. So getting back to the website here, anyone can go on here and create a login. You just basically need to provide your email and a unique password. Now this is the administrative part of the site that you need a username and login for. Just for the map interface, you don't need to log in or anything like that. What we have here is the list of fires that we've processed, loaded to the website. They date back, as I said before, to 2000. We have 2000 through 2015. And in order to actually upload data, say, for instance, the stuff that I just processed, we have a nice, easy-to-use upload button here. Now, in order to upload those folders that I had shown you, you simply can either click this Select Files option here and navigate to the location of those outputs, or we can just drag and drop. So in this case, let's just kind of drag this guy over. It loads really quickly. Within a few seconds, it will register that entire zip folder. And depending on the information provided in the shapefile, we'll hopefully have at least the name. Otherwise, it will just have the year. Most data sets now that have been kind of standardized under Ravage have the same naming conventions in the shapefile attribute table. So this stuff will typically load with what you see above, with the year and the name of the fire. But some of them are having different naming conventions. So this sheep fire, we just have to manually enter the actual year here and click save. And we'll notice that it is up here now. It's actually duplicated because we already had that one loaded on here. And we could load, tens of fires at once into this upload interface, and it will perform those uploads very quickly. Now, the next step is essentially visualizing. So now that we have all these fires up here, we can now go into the map interface, which you can access from here. So here's our map interface. Let me expand it a little bit for you. And if I zoom out, you can see the study area that we're working with overlaid on a base map. And for some locational context, we can add these national forest boundaries or HUC 12 watershed boundaries. At the moment, we don't have any sort of on-the-fly processing that is done by this tool. It is something that would really be very server-reliant. So we would need to find a long-term host for this tool that would enable us to do something like that. That's why we basically developed this desktop tool, something that you could use yourself on your own desktop and create those outputs that you could then bring into this web interface. So here we have about 3 parameters that we need to satisfy in order to start visualizing our data. First thing we'll do is just select the year of interest. So the fire I'm going to focus on today is a 2009 fire. So 2009, that breaks down all the available fires we have here. Notice we have those duplicates of sheep, but we're going to focus on this station fire. The first thing you'll see, it'll zoom right into the fire perimeter. Now that was one of those files included in the zip folder. This is just north of Los Angeles, so perhaps an area that some of you are familiar with. And next we select an ecosystem service. We'll start with recharge. And you'll see immediately that we have this sort of spinning wheel here. Since this is a really large fire, I think something like 160,000 acres thereabouts, it takes a few seconds to load up the data. Recognize that it's loading 3 different rasters. It's going to be loading our pre-fire and post-fire ecosystem service rasters. But it's also going to provide us that ravage data that we use as input. So here we can actually see those percent cover losses across that entire perimeter. And you'll notice that when we select any of these different display options, that our legend will adjust accordingly. It will rescale to the minimum and maximum values within that raster and adjust the different units used for that given raster. So now we could click in here to get more information on just individual pixels within this raster. So here we just have mostly 100% cover loss across this fire. Some areas where there's 0% cover loss, but this was a pretty intense fire burned in 2009. So let's go to the pre-fire data and look at this raster. And notice here that we're looking at millimeters per year with a max of 253. Just like we could with the ravage data, we can click within the fire perimeter to get individual pixel values. And this is not something that you're going to do too much quantitative analysis for, but if you're interested in a given area, you can look at this data on a pixel-by-pixel basis. If we look on the right side of the screen here, we can see a couple of different options we have for assessing the statistics on this fire. So here we have a basic pre- and post-fire chart showing us the provision of ecosystem services within this area. And you'll also notice that these have been converted to a different unit. Instead of looking at it on a per pixel basis, we've summarized the provision of basically water recharge to acre feet per year. It's a volumetric unit, and it is basically summed for this entire fire perimeter. So in addition to this chart, if we click this button here, we can switch over to our tabular statistics, where we have pre-fire, post-fire data, as well as how the post-fire data is broken up into the different bins of severity. If you want to learn more about basically how this data was produced, how the ecosystem services were calculated, we include this question mark button here, which provides information on how it was derived, the model that was used to derive it, as well as some of the more nuanced aspects of this data. If we are interested in looking at the post-fire data, the raster itself, we could switch our display options here and click our post-fire data and kind of go back and forth to look and see how our ecosystem services have changed. And we can see that the recharge has increased immensely post-fire. Now, the nice thing about this, the way it's kind of organized now, is that we could now stay zoomed in on this fire and start looking at other ecosystem services and assess the impact of, say, runoff in this given area. So again, it takes a few seconds. A lot of these fires are less than 100,000 acres. This one is 168,000. And again, we can see these pre- and post-fire values. The stats have updated here on the right side. We can toggle back and forth the chart in the table and look at the volumetric total within the fire perimeter. Just like the recharge, this is an acre feet per year. We have the same ravage data here, but we can then again, just click back and forth between the pre and post. And then the final ecosystem service we have is our sediment export. This is going to look a lot different simply because the sediment export data, or at least the raster, is going to look a lot different. The sediment export data is really kind of focused in river bottoms and kind of in the lower extents of watersheds. So at first you see a lot of no data here, or very low value. But what we could do is we could either kind of scroll on our mouse to zoom into areas where we see data, or use this button at the top right, which just basically enables us to zoom into a given area based on the box we use. So we'll use that just to get in a little closer to this given area. Turn it off, and then we can start looking at individual pixels and kind of assess that sort of information on a smaller scale. And again, we have all this information on the right here in tabular format. And this has been converted from metric tons per hectare per year to cubic meters per year. So another volumetric conversion that is actually done by that tool, the desktop tool, those scripts that I showed you before. Now, if you wanted to start looking at other fires, we could certainly do that. Or we could select, let's see, 7. You start looking at other fires. Perhaps, Emma, you would like to discuss the station fire statistics a bit more in depth. But you can notice right here just how much quicker a smaller fire loads. The slide fire in 2007. And it really renders really quickly and loads all of the ravage pre- and post-fire data very quickly. So we could get to this data pretty fast and kind of jump between different fires, different years, and different ecosystem services. So now I'll go back to that station fire. And I don't know, Emma, would you like to discuss these stats at all? Kind of what we're seeing here?
Hi, Eric. It's Emma. So I think perhaps what we'll do, because we're conscious of the time, is perhaps to open it up for questions, because I went through some of the methods and some of the results from my presentation, but perhaps now with you on the line, we could open it up for questions if people have specific things they want to ask about the tool. I think that'd be useful. Yeah.
Absolutely.
So are there any questions that people have, or things to clarify, or, you know, questions about how it could be used in the future? So now, Jamie, do we have the microphones today, or?
We do.
Okay.
I can speak pretty loudly.
Okay.
You can repeat it. So I know you went over this in your presentation with the recharge. I just wanted clarification again on that recharge. You were talking about recharging into the groundwater infiltration into the soil.
Yeah.
And then you were talking about, and then does this tool also know the difference in runoff?
Yes. Yes, and what we're seeing here on this screen is the difference in recharge is increasing post-fire, and that's because we've removed the vegetation, so there's no evapotranspiration. So we can see the water is going down into the ground. But like we said before, we need to be conscious of the precipitation and temperature the year after the fire, because that's going to affect those numbers. And the tool has recharge in it and runoff and sediment erosion at this stage. And the idea is that we are going to try to get more funding for this and to include the other ecosystem services as well.
So the ravage data, when it has a severe high intensity soil burn or whatever, then do you change the value of the runoff based on the fact that it's done?
Yeah, that's correct. And in the beginning, Eric showed all those files when he was going through the script to show that we've made those, we've got different data layers for each of those different cover amounts for each of the services. Yeah, yeah. So yeah, yeah. Edward, can you talk loudly? Did you have a question?
Yeah.
Okay.
Briefly, when you look at the runoff or say it's like recharge, is that somehow taking into account the hydrophobic soils that develop after the fire? You may have mentioned that.
Yeah, no, we don't. We talked about this with USGS when we were calibrating it to post-fire impacts, and that was it would be a nice addition to do, but it's not included in the hydrophobicity isn't included in this. Yeah, yeah, yeah. Lance, do you want to?
I just was looking for clarification on the pre-fire condition, so that, and how that's it's average over a certain amount of years and keep rolling forward.
The data in the tool at the moment is just showing the water year before. So some of the other data, those big maps over the whole study area I was showing to calculate total runoff over the whole area, that was the 30-year average. But for the tool, it's the water year before that's being shown. Yeah. Marty.
So Emma, for something like the Thomas fire, which was so huge, and part of it was in the Los Padres forest, so could you use this tool, would it just apply to the part that falls within the forest? So you basically, would you be able to do data for outside the forest?
So that's a really good question. So it's so dependent on the ravage data, which is yeah. And Eric, I don't know, do you have any ideas about long-term ideas for, you know, adding more processing for the ravage data if there are key fires?
What is your question exactly? I mean, are you talking about?
Yeah, there was a question that
of how ravage data is created, or?
No, it's what happens when you have a fire that's partially on Forest Service land and then on non-Forest Service land. So you've only got ravage data for part of it.
So for a fire like the Thomas fire.
Yeah. So do you think there's scope in the future to where there are significant fires to map the whole area, even off non-Forest Service lands?
Yes. I mean, I think a lot of the data already includes that, the fire perimeter. I mean, in this case, we're looking at stuff. You could kind of see just here, some of this is off of the actual national forest boundary. I think they still map it if it's not on national forest land. So they are basically using Landsat data that covers all of California. So there's no reason that they would have to clip it only to the national forest boundary, because of course, they're not only interested in that land, they're interested in the surrounding areas as well. And I know in California, I think Jay Miller just retired, but you had some folks there that would happily provide you data going back in time and go back to the Landsat records and create this data. So I don't think there would be any issues, especially with the folks that you have there in Region 5, with creating data that's outside of national forest boundaries. Now, if it's entirely outside of national forest boundaries, I'm not sure what their protocol is. I find that rather unlikely. At least some of it would probably be within a national forest. But their protocol for developing this ravage data is so standardized that it should be relatively easy for them to create that ravage data, even if it's outside of forest boundaries. And I think you have people in Region 5 that will do that on request.
Okay, thank you. Lloyd, you had a question?
Yeah, so in the case of the Thomas fire, again, like I mentioned earlier about the Ventura River watershed, 80% of the watershed is burned, 95% of the Ventura River watershed that's on national forest is burned. All the upper watershed is burned. And that watershed is very efficient in recharging the aquifer year to year, even for minimal amount of water. And the whole valley depends upon, the Ojai Valley depends upon that recharge every year to keep the water supply going, and so this year with the Thomas fire, like I said, those recharge rates were reduced to a tenth of what we normally would, because we're not getting any recharge. And that's a huge economic cost that we're not getting recharge. So without flexibility and having models reflect that economic cost.
Yeah, I mean, I think this is a good question for Laurie, because yes, the thinking already is that, you know, we're getting more runoff and more recharge after a fire. So that's a positive in terms of the economic value, but perhaps you want to add more.
So my understanding, you're saying, is there a way to are we going to be valuing the lack of recharge occurring?
Right.
That's
so
right.
In this case, you're getting recharge, which helps the aquifer. In our case, not getting any recharge in our aquifer is going to be much more deficit than normally.
Right. So I am estimating using the dynamic vegetation model. If that is reflected in the modeling, yes, it'll be valued. So am I going to do it for, like in this tool, there'll be a value, so it could be done if that change and recharge is reflected here, keeping in mind that the value I'm estimating is the value to municipal users of water. So it's not going to be to ag users or industry.
Just to follow up on that, I mean, the data that were collected that showed that were done by hydrologists, but measure infiltration rates in the river because that's what's the fire. And so they actually looked at how much water is coming down, what the rain was, and they estimate the penetration by how much water moves over. I forgot how they said, but the guy was he was kind of shocked at the reduction, and it's still really kept up. So as far as value, something, you know, ecosystem service and the value that we've lost that whole particular unique functioning of that watershed.
think that that means that, you know, the use of evapotranspiration as your metric to figure out whether or not you're improving recharge or not may not be a valid metric? That's what that's what I'm worried too.
And also, I mean, it sounds like it's a scale issue as well. I mean, we're doing this at a footprint across Southern California. It's 270-meter resolution, and that sounds like that's a lot. I mean, it's a lot more detailed. Yeah. So I think there's a couple of things going on. Yeah, but within that basin characterization model, the best thing for us to alter is the evapotranspiration post-fire. So to capture that, it's going to, you know. No, I mean, it's a great point about, you know, trying to make these estimates at different spatial scales.
But you know, when you look at the hydrologic stuff, you know, typically the bulked and burned Q, the 50-year bulked and burned Q, which is the, you know, public works metric for how much runoff you would estimate using, you know, RAS kind of models. They estimate that there's not recharge and that there's just going to be increased runoff. So that they're not looking at evapotranspiration loss as a way of increasing recharge.
Okay.
So this doesn't, what you're talking about evapotranspiration doesn't match any of the hydrologic models at all. You know, because you're saying you're going to get a net benefit.
Yeah.
All those calculations say there's a net increase in runoff, not in recharge.
And what sort of spatial area was that over, or?
It can vary.
Okay.
RAS is used on all different spatial models.
Okay. I mean, we picked the basin characterization model because it is widely used throughout the state for you know, a bunch of different applications, and so that's, you know, one of the reasons we went for that. But it sounds like different results with different models.
Well, but modeling is only so good as it's reflecting what is happening in reality on the landscape, right? So if, in fact, what's happening on the landscape, as Lloyd's pointing out, is that evapotranspiration is irrelevant here in terms of whether or not you're getting recharge, right? Because it's about the fines, you know, plotting pore space and preventing it. And so if you're modeling and suggesting that you're going to get recharge and that's going to be a net benefit, that's not matching reality.
Well, I think we'd need to look in detail about the two different models and to see, because I mean, the feds have done this over and over again, and they calibrated it using stream gauge data. So they are finding in those watersheds where they have the stream gauge data on basin discharge that they can match that flow and amount. So they did it for the whole of California across 160 watersheds to calibrate this. So they, you know, so
it is really interesting to see the discrepancy.
Yeah.
Well, you're getting increasing, so for decreasing evapotranspiration, you're seeing an increase in runoff, which is what you're looking at. And right, but that's different than what she's talking about in infiltration.
I just wanted to add that the modeling that I'm going to be using for the water estimates are coming off the MC2 model, not the basin characterization model. So it's probably, in some ways, it might be a more coarse estimate of water, but that's what I'm using mostly because I want to be able to project to mid-century and end of century to see how climate change will affect that.
Okay, Edward.
Can you just remind me, when I look at this image for post-fire, what's that time frame for post-fire?
That's immediately after the fire, when they mapped the RAVG, when they did the RAVG mapping, which is within a few weeks after the fire.
So it's like just a quick snapshot.
Yeah. But they also did RAVG mapping 1 year after the fire, and so there is an extended one. So there's potential that you could also include that. Yeah,
a lot of it depends on the quality of the imagery too. There's a lot of clouds, and that could kind of push back the immediate assessment for the extended assessment.
Okay, Jamie.
So it sounds like taking what Lloyd was saying and you were saying. It sounds like maybe you could add into the models a little bit more about particle size and a little bit more about not soil erosivity so much as but particle size and then hydrogeology, some basic soil characteristics that might help
Yeah, it does, but the basin characterization model includes soils and it includes bedrock. So it does account for bedrock and soils, which is why it can produce this spatially distributed outputs on runoff and recharge. So those components are there, but perhaps what we're hearing is they're not fine enough scale because these are 200 centimeter pixels.
The scale is that they're not, the basic characterization wasn't built for post-fire situation. I think that's what we're saying is that if you remove biomass without fire, then the basic characterization model applies, and it's backward saturation driven change in recharge. But if you have a fire, you're changing that infiltration, so the basic characterization in its native state doesn't necessarily apply.
Yeah, you're changing soil properties, and those are static and these.
Right.
Mhm.
So, but this is a great question for the Flynns. Maybe there's some way. I mean,
That they can include
like you said, they're training that model with actual runoff data. Maybe there's enough post-fire watersheds that they could use to refine that part of the model.
Yeah.
But it is something that should be incorporated if this is being used for post-fire.
Yeah. Okay.
Especially trying to get value.
Right. Yeah, Ali.
Just back to the value estimates, I was wondering if you are planning on including increases in urbanization below, which may change the way people value water, because with increased urbanization, water becomes more scarce for the individual, per person basis, and maybe the value goes up.
That's a really good point and really relevant to this highly urban populated area. What I am doing, I'm just saying values as of today for using 2017 dollars. So even though I'm getting projections of how the quantity of water will change over time, I'm only denominating it relative to people, the number of the population today. There are population estimates, it just gets more complicated. So this is the first run. So not now, but perhaps in the future, but this is just a first step because as I said, when I first started the project, I'm thinking, great, there's lots of stuff around. There's actually, there's not much around. So as a first step, this is just where we're going to start off at.
And the idea is that in the next stage of the tool that there will be an area where you can look at the economic or cost values associated with these changes in services.
Oh, sorry, I should add that the dynamic vegetation model, that it's running under certain RCP, so it is taking account population growth inherently there, but so that's in biophysical part, but the actual economic values I'm doing just to today's terms. And really that's partially just to make it easy for land managers. If you're trying to think, is it $2050 or like $1999? And so we're just trying to make it an even one for people to see today, which is why it's important to update these values because inflation and things change all the time. So we need to account for that.
Okay, what do you want to do about timing?
Right. So my fear here, this is a great discussion, but I fear that for the field trip, we'll be getting back really late if we don't stick to our schedule. So maybe while we start getting ready for the field trip, I see Jim and Aaron both had their hands up, Noah. Maybe we could do individual questions for Emma and Lori, and the rest of us can start making sure that we have our gear together, water, lunch, and those of you going on the field trip, those liability forms are really important. They're on the back table. I could show you where those are, and we're going to start loading in vans to try to get out of here in the next 10 minutes. Oh, the video.
Eric, thank you very much.
Eric, thanks so much for being on. We appreciate it.